We're supported by the ASC program in the NNSA and have a nuclear stockpile stewardship mission. I'll talk about some of the motivations for why we chose the Sierra architecture, and then some of the application preparations very quickly. But again, I really want to get to some of the open science results and do my best to convey the work of many other great scientists at the lab who have taken advantage of this system so far. And then I'll wrap up talking a little bit about our view of AI and how this fits in and how we plan to use the machine and develop our applications in the future as well. So Lawrence Livermore, we're nearby. I drove over here this morning, so it's about a 50-mile drive over the hill to the east, about a square mile right on the edge of the Bay Area, literally hills to the east and south of us for tens of miles. So we are right on the fringe of the urban Bay Area, really. About 7,000 employees in a square mile site. As I mentioned, we're a national security laboratory, sort of based in nuclear security, the weapons program, but supporting all of these different activities from HED science to materials and manufacturing to even earth and atmospheric science, of which there are national security concerns there. The point here is that all of this at the laboratory really sits on a foundation of high-performance computing. We like to say that HPC at the lab really touches every corner of the laboratory and impacts all of the missions there. So nuclear security is about stockpile stewardship, understanding the safety and surety of the weapons that we have, really because we can't do testing anymore, and we want to have a reliable stockpile. Looking at things like life extension programs, and really all the underlying science that underpins the stockpile stewardship program. The analogy we use is you could think of a weapon as a very high precision machine, not like a race car, but let's use that for an analogy. And we want to do things like maybe remanufacture some parts or maybe improve the safety and security with something that looks a little bit different. Under treaty, we can't provide any new capabilities, but we do want to make these systems safer and more secure. But the problem is, unlike the old days, we can't take it out and actually test it. In an underground test, for example, akin to you've got this high precision race car. You know that when the day comes, you want it to work and you want it to win that race, but you can never turn the key. And so what sorts of things do you need to do to ensure that it's going to work without ever being able to turn that key? That's kind of the analogy we're looking at, and that's where simulation, along with experimental facilities and other science, provides a key role. And it's more than just nuclear weapons. It's understanding non-proliferation. It's understanding are the rest of the world following treaties, counterterrorism, et cetera. And of course, all this relies on application codes and designers who run them, and a deep stack of technologies, tools and visualization and file systems. Facilities I'm not going to talk about, but a system like Sierra, you don't just plop down in any old building. Our current facility is being upgraded to support 85 megawatts of power, so we can support 2 Exascale class systems at the same time. And then, of course, the computers, and that's what I'll focus on today, is specifically the Sierra system. This graph is just to show, going back to sort of the need for simulation and stockpile stewardship. The red bars here, this is on the x-axis going back to the end of World War II. The red bars are the number of underground tests that the U.S. performed, and the blue bars are sort of computational power that's been at service in the program. And you can see, not unsurprisingly, when we stopped testing, we needed to really accelerate computing. And the ASCII program, the Accelerated Strategic Computing Initiative, is really what helped bend this curve here and make high-performance computing the thing that underpins stockpile stewardship like it does today. And why do we need more and more power? We're always getting faster machines. It's a voracious appetite. There's really 3 axes here. We're always trying to improve the physics and have better models that give us predictive behavior along the top. We're trying to obviously do things at higher fidelity and higher resolution. And we're also trying to do uncertainty quantification. So it's not like you can just run one big simulation that takes a month or 2 and say, yep, that's the answer. There's a whole science around running ensembles of calculations, understanding all your uncertainties, modeling all of those so that you can put an error bar in your simulation just like you would in an experiment. And all of those three axes combine to really drive where high-performance computing needs are in stockpile stewardship. This slide I stole from Eric Strohmeyer. You may have seen this if you go to the SC or ISC conferences. It's just to show, this is showing over time since the beginning of the top 500. They took sort of the normalized HPL for each 6 month or each list, and who had the major systems there. And Livermore, really since the 50s, long before the top 500 list, but especially since then, somewhat dominates this list right now. And the Department of Energy here in the U.S. really in total makes up a good chunk of this list. Now, what doesn't get captured here is, this is changing every time, and countries like China and others are slowly catching up. So let me give a quick overview of the Sierra system. You can find out a lot more information online about this, but in a nutshell, it's a 125 petaflop peak system based at Livermore, as I said, supporting our national security mission. This is the building that it's in. This is the office side part of the building. My office is somewhere in the middle there, behind that glass. But the little more detail on the system. So I already mentioned 125 petaflop peak. Each node, of which there are 4,300 of them, is run by two IBM Power 9 processors, so a new very powerful fat-core CPU, and 4 V100 NVIDIA Volta GPUs. Each node also has 320 gigs of memory, 64 of that high bandwidth memory on the device, as well as DDR4 CPU side memory. And then each node also has 1.5 terabytes of non-volatile memory for use as a burst buffer or as a way to spill over some of your memory if you need more memory. I'll mention quickly the Summit machine, which is the current #1 machine in the world at Oak Ridge National Laboratory. Very similar architecture. The key difference here, it's actually got about the same number of nodes, but each node has 6 GPUs instead of 4. So the ratio of CPU to GPU, we made some different choices there between Livermore and Oak Ridge. So as a result, even though their system is about the same number of nodes, it's 200 petaflop peak system. So just drilling a little bit deeper, the GPUs, if you do the math, there's over 17,000 of them. That's a lot of horsepower right there. That's an impressive number. You think about a DGX box that NVIDIA sells with all that power, and multiply that by 1,000 or so. So this is really where all the flops, or most of the flops in the machine, most of the computational horsepower is coming from those GPUs. There's a high-speed NVLink between the CPU and GPU. So the Power 9 actually has support for NVLink. So not only do you have NVLink between the GPUs on a node, but between the CPU and GPU, which as these GPUs get more and more powerful, that ratio of, if we were to use PCIe, for example, that ratio would just exacerbate the issue of trying to get data back and forth off the device. The CPUs I mentioned are all IBM Power 9 processors, including the front-end nodes. And the memory is, I already mentioned a little bit, and of course all of this sits on top of a Mellanox interconnect. Let me skip this. This is just a diagram and a little detail on the Power 9 processor, but 24 cores and NVLink 2, big caches, really nice chip. And the Volta itself, probably most people know this, but it's over 7 teraflops per GPU in double precision. Single precision is just about double that. And deep learning, what this means, if you can use those tensor cores that are a new innovation, you can get pretty impressive floating point operations there. So we're still working on figuring out how we can best use those. Oak Ridge actually had an interesting calculation, I think in genomics, where they were able to use those tensor cores quite effectively for some simple small matrix operations not related to graphics and deep learning and the sorts of things that those tensor cores were designed for. So I think there is big potential in the future as we learn how to use new innovations like this for science. So we have a companion system called Lassen because Sierra, just as of a couple weeks ago, has now transitioned to the classified network at Lawrence Livermore in service for the classified mission that I talked about earlier. But we do have, every time we get one of these big systems, we use other funding, institutional funding, and some other sources to field a baby version of that system on the unclassified side for use in open science. So that's going to be named Lassen, which is a peak in Northern California for those who don't know. Bottom line, it's very similar. It's just 1/6 in size. So this system, so we have a similar configuration with our previous set of systems. So you may have heard of a Sequoia, which is our large Blue Gene Q system. There's a companion system there called Vulcan that's 1/4 the size of Sequoia. So basically Lassen is a little bit more powerful than even Sierra was. So we're trying to keep our unclassified systems sort of at the same power as our most powerful systems that we're transitioning out. Just a few obligatory pictures of the installation. This is probably what the machine room floor looked like about a year ago from now, maybe a little more. A lot of work to put this in, but if you visit now, you see a nice shiny room with nice blue lights and blinking lights and banners and signatures of the Secretary of Energy and all that. But a long time to install something like this, as I'm sure this audience knows well. So let me talk a little bit. I think most people understand this, but this was a pretty big deal for Livermore to make the decision to move to heterogeneous computing. So I just want to touch a little bit on what drove our decision there and how we've approached that. So this is a chart that, again, going back to the early 50s, sort of the advent of scientific computing, showing some of the peak systems. These are not top 500 numbers. These are mostly machines fielded at Livermore and Los Alamos primarily, some at Sandia. The point here is that there's a couple distinct eras of computing. Like back in the beginning, it was just serial programming and mainframes. Then vector machines came along, CDC and Cray, and people converted their codes to write to that. And then there was, the distributed memory era, which we're still in, sort of amplified by, MPI standards and things like that. And we've known for a while that, pure CPU and distributed memory scaling wasn't going to be able to necessarily take us to exascale just because of things like power constraints, which I'll talk about next. So there's something coming next. Could be the many-core era. I think it's pretty safe to say it's going to be called the heterogeneous era, as we look back on this, because it's really hard to see a path forward to the kinds of improvements that this chart represents without doing something heterogeneous. So a lot of that is driven by, like I said, power constraints. You could field, a 125 petaflop CPU-based system, but the power requirements would be through the roof compared to what we're using for Sierra. I'll just note Sierra draws about 11 megawatts of power peak, which is actually about the same as the Sequoia system before it, the Blue Gene Q system, which itself was known as a pretty energy-efficient architecture. We have lots of large Linux clusters, and just energy efficiency-wise, they don't hold up quite the power per dollar of science or per flop, if you will. So this is all trickling down. Obviously, hardware designs are reacting to this, trying to figure out how to be more efficient. The software needs to support much, much more parallelism in core. We call that in-scaling, whereas outscaling is can you get your problem to run on more and more processors like a Blue Gene system. Something like a heterogeneous system typified by GPUs, it's really about can you uncover all that power that's sitting on a single node. For example, Sierra's 4,300 nodes. The Sequoia system before it was over 16,000, right, with 1.6 million cores in it. So very different architecture for us. I think most people have probably seen this chart a number of times. It's a great chart that shows Moore's Law, at least for now, appears alive and well. Single thread performance is kind of barely hanging on, but the innovations are running dry there. Clock frequencies have been flat for quite a long time now, coming up on 15 years. The power that you can put into a socket is mostly flat, and so where things are happening to keep chip designs going faster and faster is really in the number of logical cores or threads, or in GPU context, the number of SMs and threads that you can drive. So this is just to show that we've been talking to vendors and thinking about the system that is now just being turned over to the program for, I think, going on 6 years now. So we have a very long-lived cycle where we'll start talking to vendors and understanding, letting them understand what our needs are and understand from them what their roadmaps tell us. For the Sierra system, I think those conversations started in 2012, sort of began in earnest in 2013, and by early 2014, the RFP was on the street. This was part of something called Coral, which is a collaboration with Oak Ridge and Argonne and Livermore. It's an acronym. And so the three of us went together for this large bid. You may remember at SC19, the system that became Summit and Sierra were both announced. And so we've been doing a lot of work over for 4 years, almost 5 now in the meantime, and the system will take us through to the mid-20s. But we're already, not only do we have Sequoia still on the floor, so we're still getting good science use out of the last system, but we've already been in discussions and had the RFP for the next system beyond that. So at Livermore, it's a system called El Capitan. It's scheduled to be the first Exascale system in the NNSA. Oak Ridge and Argonne, as part of the ECP, are supposed to be getting some systems about a year before us, but we're going to draft them and hopefully get a nice, robust system there. I can't say much about what that's going to be, but hopefully there will be an announcement this spring. So let me shift a little bit to talk about the application space. So I talked about the need for weapons and weapons science, and that's really a multi-scale problem, down from ab initio physics all the way up through the continuum and understanding full system design. We've got a large set of codes we call integrated codes because they're multi-physics. They integrate a large number of different capabilities, tightly coupled. They're typically on the order of 1 million lines just for the base code, plus millions of lines of third-party libraries and such. But these are some of the unclassified applications that we can talk about that we're interested in. I'm going to talk about inertial confinement fusion a little bit more later, or ICF. Things like high explosive cook-off, that's what HE means there. So if I slowly heat up a canister of high explosive, over time, does it detonate? Does it deflagrate? Does it fizzle out? That's important to know, for example, if there's a weapon in a fire scenario or something like that. So these are modeling things on hours and days sorts of timescales. Additive manufacturing is a big new area. We're trying to understand, can we additively manufacture some of the parts that we need to replace, and what are the implications of the various designs. This is an example of laser melting in a powder bed. And so I hinted at this. This is a Sierra system, is a big 180-degree shift for us. We've been a blue jean shop at Livermore for a number of years, going back to the first BGL system in the early 2000s. I think I alluded to this as well, looked into our crystal ball and decided that heterogeneous computing was a path we needed to get ourselves on, and it was a good time to do it. And so that's really been the focus of effort at Livermore in the program for the last 3 or 4 years, is getting ready for this day when Sierra is turned over. And I think it's safe to say we're successful. We're very happy with the machine. It was not easy. It was quite a lot of work, but it's going to pay off for us. And so part of the way we did this was something a little bit unique for the NNSA labs, which is we partnered with the vendor community that were providing the machine, in this case IBM and NVIDIA. They've got application expertise in-house. They've got dev techs at NVIDIA and folks at IBM Research who really understand applications, and they understand the hardware. So we got them in working with us side by side with the goal of helping us get our codes ready for this next-gen platform. And also thinking about performance portability. I skipped over that a little bit. So the high-level goals, we call this the Sierra Center of Excellence. All the other labs have similar COEs, we call them, and we get together and share info regularly. We've had some performance portability workshops the last couple years that sort of spawned out of all these different COEs working together. But really, we wanted to train people. We wanted to have our applications using the advanced features on these systems. It would be a drag if we put an application on Sierra and only use the CPUs. That's not a good use of that system. And we also wanted, use the features like the non-volatile memory and the new interconnect features, et cetera. But we got to be performance portable. I alluded to this. We've got clusters. We've got other machines at Los Alamos and elsewhere that we have to run on. So we're not just going to rewrite our codes in CUDA, for example. And then really to continue building strong ties with our vendor partners. So ICF, I talked a little bit about. This is the basics of it. You've got a little canister about the size of the end of your pinky from the knuckle on down with a little tiny pellet inside about the size of a BB made of DT gas. The National Ignition Facility at Lawrence Livermore is one of the biggest science experiments going in the country right now. 128 laser beams in a basketball stadium-sized building that all converge on that little BB-sized pellet to try to get a perfectly spherical implosion with the goal of getting more energy out than you put into it, fusion energy. Obviously, you can do 1D approximations like on the left. 2D is a little bit better, but you really need to be able to do 3D calculations if you're going to understand what's going on there. And I've got an exemplar calculation later I'll talk about. So really what Sierra is allowing us to do in programs like ICF is to think about running 3D regularly. We've always had 3D capabilities. It was always a pretty heroic kind of run. It could take a day or it could take the whole machine for a dedicated weekend if you wanted to run ensembles. Now we're at the point where we can really do 3D regularly and with relative ease compared to some of our earlier systems. And that's going to be critical to getting the science understanding. I won't talk about this much, but we're also in anticipation of not only this machine, but the Exascale machines in general, developing a whole new generation of codes in the program. Our bet has been on high order techniques. We think that while they're more floating point intensive, the computational intensity is higher. You can bring data in, crunch on it a lot more. It's, as memory increasingly becomes the limiting factor in these architectures, we think and are seeing that higher order methods are one way to overcome that. And I've got a whole other talks on this and would be happy to give those some other time. But now I want to shift to some of the early science applications as promised. So what do we mean early science? So early science is that time frame between the time the machine finally gets installed and first boots up, which was just under a year ago. I think it was about last March, until the time it's unplugged from the unclassified network and transitioned to programmatic use. So it's about a 10 or 11 month period or so, but we get some friendly users to help shake down the system. It's not a fun job. It's not a fun time. Anybody who's deployed a big first-of-a-kind system, I think, gets that you're dealing with buggy or incomplete software and bad nodes. You have to find the needle in the haystack. It'll reboot on a whim, and operators aren't always going to tell you what they're doing. It's a tough job. But the benefits are, and when it is up, you can get pretty much a whole machine dedicated to yourself and do some pretty amazing science. And so that's the carrot here for early science. So let me start by talking a little bit about some earthquake simulations. Those of you here in the Bay Area know why this is important. We want to be able to model earthquakes in a number of different scenarios, model the ground shake, and understand where the most vulnerable buildings are, for example. So this is Artie Rogers at the lab. He's done most of this work. There's some work with this code going on at Lawrence Berkeley as well. But this is this square here is. I'll show you a movie in a minute of one of the early calculations we did. But obviously this is the San Francisco Bay Area, so we're modeling about 100 kilometers. But if you want to model earthquake motion at high frequencies, you're really getting down into the 10 meter resolution range. So these are really big and complex problems. And what you're looking at here is the domain they covered on the right and some of the rupture models used on the left. I'll just play this really quick. It's a little hard to see because it's rotated sideways, but you've got the San Francisco Bay here. North is that way. You're somewhere about down in here in Palo Alto. Livermore is up there in the upper right. You notice some of these waves get in between these mountain ranges and sort of ring around a little bit and get funneled in. So these models actually take the real geography of the region into account to do this. Now, that's great. You can do one of these calculations, but you don't know where an earthquake's going to hit. You don't know what the magnitude is, so you really need to be able to run hundreds, thousands of scenarios and try to gather all that data to make the most sense out of it. So the calculation you just saw was first run on Cori, which is a large Knights Landing Bay system at Lawrence Berkeley. It's the number 10 machine, I think, right now with a 27 petaflop peak. And we did some runs of this on Sierra just recently, which you know about. This is just to show basically the exact same problem setup, but the key here is that this was a dedicated run that used 85% of the Cori machine. We're able to use just 256 nodes, or 6% of the Sierra machine, to turn the exact same problem around in just 10 hours. So with that sort of turnaround and not needing to be a heroic take over the machine type effort, this is going to allow earthquake science to really advance. This is just to show the two calculations matched almost perfectly. This is, yes, just an eyeball norm, but there are some scalar values here that show their exact answer out to 10 significant digits or so. And likewise, just comparing the two calculations. Just if you know your code is validated on a CPU architecture, it's nice to know that you get the exact same answer when you switch to something like a heterogeneous architecture. So this is just to show that these are different frequencies that you model at, ranging from, I think, just over 1 hertz up to 10 hertz. And, obviously what you see on the top, just I don't have the actual seismograph here, but you can just kind of tell you're getting a lot more detail and resolution there. You're missing a lot of the features, especially in the initial shake if you're running at lower resolution. So running these at higher frequencies, I should say, is key. And every time you double that frequency, you're adding about 16x in computational horsepower. So we're trying to go even further. This is, again, just to show that it matches some empirical models. We're trying to go even further. Artie wants to run on the Summit system, take over that and do something on the order of a 16 hertz frequency calculation. I'm not going to go into detail on the slide because I'm running a little bit slow, but just to say that it's largely scaling with the total amount of memory available on the system. So switching gears a little bit, we've got a project at the lab related to the Cancer Moonshot Initiative, and initially through the National Strategic Computing Initiative to have this whole of government approach. So the idea here was, let's take the supercomputing prowess that the Department of Energy has and begin to apply that to other agencies. And in this case, the National Cancer Institute and Frederick Labs stood up and said, we've got some problems we think we'd really like to understand some of the fundamentals of how cancers form, particular cancers. And so in a nutshell, I'm not going to go into much detail on this, but there's a protein called RAS that attaches itself to a cellular membrane. It's only effective if it's attached to a membrane, interestingly enough. But what its job is to basically signal growth. And so there's a whole pathway here in biology that this thing says, okay, you need to split and grow. Now, if there, some kind of defect in the pathways that gets stuck on, you have uninhibited growth, and in particular, the kind of cancers you see on the left, which are some of the most nasty cancers, pancreatic cancer, for example. 93% of pancreatic cancers are of this type. There's no known cure for these. So this is a grand challenge problem for folks like the Cancer Institute. And so our goal was, well, if we can understand some of the fundamentals about how these RAS proteins work, maybe we can find something to inhibit those pathways. But the interesting thing here, yes, it's interesting science, but from a computer science standpoint, this is a classic multi-scale problem. So you're trying to model a membrane at relatively long time scales, milliseconds and microns in length scale. But these proteins that you're modeling, these RAS proteins, these are molecular dynamics calculations. And if you know, thinking about molecular dynamics on anything more than extremely small time and length scales as a non-starter. So the goal here was, well, let's do multi-scale modeling. We're going to model the membrane and the RAS with an approximation at the micron scale, model the proteins at the molecular scale, and really try to understand how these things are dimerized, for example. So this is just a movie showing, this is the membrane, the colors in the background, the blues are just a particular kind of lipid concentration, and the little blue dots are these RAS proteins that we're trying to model. Now at this scale, they're modeled just as sort of simple approximations. But what you want to do is understand now which of those are, quote, interesting. And the definition of interesting is a little bit complicated for us non-MDs. But basically the way they determined that is they trained a data set using a reduced order model with about, I think there were 15 degrees of freedom in this model, or 15 free parameters. So developed that model, and then each of these squares basically passes off to that inference engine and says, tell me what's interesting here. Sorts those, and then uses that to spawn off a detailed molecular dynamics calculation here. So what you're seeing here is a much more detailed representation of that membrane with the RAS proteins on there. And then in real time, in situ in the machine, we're running these calculations with a molecular dynamics code and feeding that back into the continuum calculation. Now this is a big orchestration problem. You're spawning new jobs dynamically. You've got machine learning in the loop with inferencing engines. So this was in itself kind of a big innovation and something we're really excited about, because I think this is the future of HPC. How can you couple all these different systems together, build new capabilities in a slightly more loosely coupled way on these complex workflow frameworks? And so there's a new hierarchical scheduler called Flux that's being developed at Livermore, which, while still not quite in production, turned out to be invaluable to helping manage all these different jobs and calculations. So this was quite a heroic effort, and they did all this, much of it back when the machine was just being turned on and quite unstable. Very preliminary results. These guys are getting very excited because they are starting to get some insight into what's going on here. Again, I don't want to go into much detail, but this particular lipid is highly charged. So are these RAS proteins, and so that's what keeps the protein connected to the membrane. Are these charges? And what you're seeing here are not the RAS proteins themselves in these blue dots, but really the imprint that they're leaving on the membrane. And if you look really close, you can see there's some unique halo type patterns here. And what this is beginning to give them an insight to is how these things dimerize, how they connect, how they actually begin to generate those pathways. So we're not curing cancer yet, but we're starting to get some insight that we did not have at this point. Let's see. So basic science. So anybody who went through a physics class in college may know that neutrons have a known lifetime before they decay, usually into protons. We think it's about 15 minutes, around 881 seconds, but we don't know exactly. Turns out to be very hard to measure experimentally. There's a couple different ways, the bottle and beam experience to measure this. Basically the bottle, you put neutrons in, and after some time you count how many protons are there. The beam, you're shooting things through and seeing how many neutrons come out. But these experiments themselves have uncertainties and they don't quite agree. And trying to determine which of those is right is important because it may be that neutrons are actually decaying into some particle we don't even know about, something other than a protein, for example. So that's a big debate in the community now. Why do we care about the lifetime of a neutron? If you think about, the seconds after the Big Bang, a sea of neutrons that were devolving into protons, finding each other, creating hydrogen and helium, the basic elements of the universe. The lifetime of that neutron is a very important number to know if you're going to model things like, the creation of the universe. So again, very basic science, but a very difficult problem. It's a little hard to see here, but the error bar is off to the right of this chart. There's some experimental data here from those bottle and beam experiments with their error bars. And they did this calculation, got that blue dot with what looks like a pretty big error bar. In fact, those error bars are about 4 times smaller than the best previous science that was done. So this is a big step into moving toward really understanding some of this basic science. And I'm running a little behind, so I won't go into detail here, but suffice to say that the way they did this was running a lot of different calculations over a large number of parameters and shrinking the error bars on all these different cases. And in fact, in the red circle on the right here, this is the new data they got. So you can see the error bars are quite a bit smaller here. The aggregate of those are what went into that previous calculation. But there's a new blue point here at a much smaller time scale. They couldn't even run that before. They had a system like Sierra. So pretty exciting results. I'm at Stanford, so I'm going to give a plug to the Stanford PSAP Center. I don't have much that I can say about this because I just had to pull some of this off a poster of theirs. The PSAP is the Predictive Science Academic Alliance Partnerships. So the NNSA funds these large centers at half a dozen universities around the country, basically to take on big science-type problems in a multidisciplinary environment, just like we like we do at the labs. And so it's a training ground for us. It's a chance for the centers to take a little bit higher risk on things. Stanford's doing some interesting work in radiation transport, I think it is, and building a whole system, the Soleil-X multiphysics solver on top of Legion. And I'm not going to go into details here other than to say we did use this open science period to try to give folks like our university partners access to this machine and begin to get use out of it. And in the future, they'll use that Lassen machine to further refine some of these results. So back to ICF a little bit. This is not an ICF calculation. This is just a simple Rayleigh-Taylor calculation, which are fluids of different densities and how they interact with each other. Lots of instabilities, turbulent growth, et cetera. So understanding this sort of turbulent flow is kind of key to the kinds of things that we're trying to understand, for example, in ICF calculations. So this was the first simulation. The reason I'm highlighting this is this one we used the whole machine for. We didn't do an ensemble with a few hundred node jobs. We took over the whole machine just to see how far can we push this. So this was a 98 billion element simulation. That's in an L code, not an Eulerian code. So that's a pretty large number of elements by any measure. We used CUDA underneath, but we have a programming model called Raja we've developed at Livermore. You can go on the web and check it out, but it's basically our performance portability layer to give us access to things like CUDA underneath or vectors on other machines. And then the visualization here was all done, or largely done, in situ with a new tool called Ascent that's part of the Exascale computing project funded efforts. Let me skip this. This is the lead up to a lot of different work going back to the beginning of the decade. Evil, DAX, and Piston were 3 different projects aimed at making VTK run fast on multi-core architectures. Those all merged into something called VTK-AM, which is now supported under the ECP again. There's a few other products here. Long story short, a lot of things came together to finally make in-situ analysis and visualization possible. And we can do this. We've demonstrated it at scale. Yes, it helps us definitely overcome the I/O bottleneck. We could never have written out all the data that we did to generate some of the movies here to the file system and done this purely post-processing. So again, this is just an example of where we're going with this machine more than it is the science itself. And this is just, a close-up pretty picture of the kind of detail you're seeing. This is actually a 3D picture. You're just looking at a slice of it through the middle. So last thing I'm going to talk about, AI is in the name of the HPC Advisory Group, so I want to give a little bit on our view of where AI is taking us, because we do have a whole lot of AI-ready GPUs on the Sierra system. We're, of course, using them for some of the more traditional HPC, but we're very interested in understanding how we can ride this wave in AI to the betterment of science. So we've got a couple initiatives going on inside the lab, cognitive simulation, intelligent simulation, depending on what you want to call it. But it's ways to think about how can we use machine learning in combination with traditional simulations, and in fact, even using techniques to feed back data from experimental data in real time. This is a quick glyph of a oblong ICF capsule. So ICF, I've talked about that BB-sized thing we implode. Everybody always thought that thing has to start out perfectly spherical if you're going to get a spherical implosion. We did some calculations here and trained up a model, and then used an inference engine to try to explore the space of all the different parameters, and it actually popped out a design for us to try that was non-spherical. So it was oblong with higher densities at the tails, like you can see. We haven't actually shot this. We can't confirm that it was right, but what it showed us was, oh, wow, these techniques can actually get you thinking out of the box. And I think we're seeing that all over the place in AI, whether it's how AlphaGo plays the game compared to the best humans. It's really a way to get you thinking out of the box. I like to think of this as AI-based computing is all about you got a lot of data, right? Whether it's ImageNet or the internet, whatever, you're funneling that down to try to get some small amount of insight. On the flip side, HPC, we're generating tons and tons of data, most which we never look at, right? We might get a visualization or a couple scalar values, but we're generating a lot of data. So the hope is that we can turn this virtuous cycle on itself, actually use some of these AI techniques to take a look at all this data that we're generating in situ, on the fly, and provide us some insights. All right, I'm almost out of time, so let me skip a few slides here. I just want to say there are some open research questions if you're going to use AI in science. So number one, physics constraints. What do I mean by that? If we're going to use a trained data set and inferencing in the loop in place of, for example, a subgrid model, those laws have to honor things like mass and energy conservation, right? These models are often very fuzzy. That's great if you're doing image analysis or trying to do voice detection, but if you're trying to model the physical world, you're constrained by a whole different set of rules. We often have sparse data. We don't have data sets as large as ImageNet, for example, and so we need to figure out how can we build usable training sets with less data. Can we explain this, right? We're scientists. We want to really understand, why did I get that answer? That's a big issue overall in AI right now. Yeah, it works. It looks like it worked. It gave me an answer that's plausible. Why? Especially when you start, going into deep learning. There's a few mysteries yet to unfold there. And then we've got all this data I mentioned, but we don't have any standard way of collecting it, of determining provenance, and specifying it. So these are all some open challenge problems that we're beginning to take on in the NNSA. Let me skip this. I'll just say real quick, we've got a couple partnerships in place. Atom is up here in the South Bay in San Francisco, partnership with GlaxoSmithKline and UCSF and the Cancer Institute, looking at using HPC for drug design. So this is an open public-private partnership. There's information on the web. Again, taking some of the expertise we're developing at the lab out to examples like precision medicine. We've got another project on advanced analytics for nuclear proliferation detection. So there's a lot of signals out there that we can use, the analyst world uses. A lot of it can be hidden and hard to detect, but we're looking at ways we can marry all that together to see things we may have missed otherwise. And finally, we've got a new data science institute at the lab. It just got stood up, I think just over a year ago or so. But this is really acting as our hub for data science activity at Livermore. We want to strengthen our workforce. It's getting harder and harder to get people with this skill set into the labs. We think, we know we've got some of the most interesting problems going on. If you love science and you love data science, then take a look at the national labs, because we're not just trying to generate more ad revenue, with AI. We're trying to solve, world-changing problems here. So that's part of what the Data Science Institute is all about. We've got a seminar series. If you're interested in coming out to the lab and giving a talk on the work you're doing in data science, hit me up, and we'd be glad to invite you out, show you the Sierra system, and learn more about what we're doing. And there's a summer institute. We get a lot of summer students out there as well. So in conclusion, I talked about the 125 petaflop system being stood up. It is now on the classified side and supporting that mission. Get yourself a Q clearance and come work at the lab, and we'll tell you all about it. But until then, that's all I'm going to say. It was a big pivot to go to heterogeneous computing. I think unequivocally we're going to say, yes, it was the right move. Everything we see going in the future, heterogeneous computing is here to stay. And if you don't get onto that track, you're probably not going to be on that up and to the right slope as steep as those of us who are. I showed you some open science results, very cool stuff. That was probably only half of what I could have shared. So there's a lot of good work going on there. You should take a look at what's going on at Oak Ridge with Summit as well. They've got some similar stories. And AI, we're paying attention to it. We've got a system that supports it. We've got codes that need it. We've got expertise interested in learning about it. And I think really this marriage of HPC and AI, it's a real thing. 5 years ago, we were all worried about architectures diverging and going in different directions, and were data science systems going to support the HPC world? I think the answer now is we can get along. There's actually a huge amount of synergy there between the two worlds, and so I hope that's part of what we'll get to talk about this week. So thank you very much for your time. Sorry, Sydney, if I went a little over. Thanks. Okay. Yes?
I'm curious how you think about AI and machine learning as opposed to expert rule-based systems. Do you see them as complementary? Do you see rule-based systems diminish?
So the question was, how do we look at AI-based systems versus rule-based systems? I probably don't have a good answer for that right now. We've not done a lot of work in the latter. We've really mostly focused in the last couple years on sort of some of the traditional AI techniques. So I'm sorry I don't have a better answer for you. I'd have to learn a little bit more about the rule-based systems world. So, yes?
So I've been through a number of generations that you've kind of worked on the history of developing systems and so on. And one of the things you've shown is how people who write the algorithm write it for the hardware. There's been a lot of talk about the core design and so on.
Sure.
Do you feel that the application, the algorithm people have any impact on how the future generation of hardware will come out?
Yes, great question. So just to summarize, co-design, is it working both ways? So definitely applications have had to react to the hardware changes. I think the question is, are we seeing impact on hardware designs influenced by the needs for algorithms? And I think the answer is yes. It's certainly not as much as, for example, the deep learning world is impacting architectures. There's not startups up and down Sand Hill trying to create as many new chips for HPC as there are for deep learning. But definitely programs like Path Forward, which the DOE has funded, were aimed at really advancing some of the hardware research, before things were taped out, before things were designed, largely informed by the work that we're doing with proxy apps and open science. And we have seen examples of designs and chips that have been influenced by that work. So I think the answer is yes, we do see that. It's never as much as we would like. But at the same time, I often get asked, if you could design the perfect chip for your application, what would it look like? Well, my application is everything from explicit hydrodynamics to linear solvers to particle transports and everything else. It's really hard to think about how could you design hardware specific to an application unless you're thinking about something like the Great Machine was designed for, or very specific. So we're informing vendors on things like register pressure is our bottleneck, or integer operations are our new bottleneck, or we need more memory channels, and that does feed back into designs. Yes?
You were worried about the divergence between HPC and AI architectures when in fact they're merging. Do you have thoughts about people who have maybe criticized AI in the US, they're coming from Asia, they're focused on quantum computing?
Mm-hmm. What was the question?
They're focused on quantum computing.
Do I...
Oh,
well, okay, so quantum computing, definitely, and I didn't talk about it. We've got a number of efforts going on in that area as well. I don't think quantum computing is going to replace HPC and AI computing anytime soon. I think there's a few interesting areas where it's going to emerge and be effective, but it's not a general purpose system. So I think it's somewhat orthogonal. It's definitely, the US needs to be putting a lot of research there. There's a new quantum initiative that hopefully will generate some funding in various agencies and some coordination across the U.S. So I hope the U.S. is going to lead in that space and not follow. But I don't think it's wrong to criticize or it's right to criticize the direction that the U.S. is taking with HPC and AI right now. I think we're really leading the way and coming up with systems that cut the middle and support both fields. Yeah. Mm-hmm.
Would you say that positive aspect would translate to a much smaller system, or is it
to a much
smaller
system?
Is it a matter of scale? So if you go to a smaller system, is it a size below which it doesn't make sense to?
That's a good. So in a nutshell, would we still be as excited about all this work and success we had making the switch to heterogeneous systems if we didn't have a huge system, if we had some smaller systems? And I think the answer is yes. I don't want to get too much into the weeds, but one of the things that we've seen GPUs really excel at in our world is being able to do high fidelity three-dimensional calculations. And it's largely because just the amount of work that you want to get on a GPU and crunch on needs to be very large to overcome some of the messaging overheads and such. And so even being able to run modest scale 3D problems, scale them out in things like ensembles, this is going to be an exciting direction for us, because even with smaller scale machines, we're going to be able to do things that otherwise would take a large percentage of a major cluster, for example. So I think the answer is yes. We're going to not only see the benefits of this at extreme scale, but I think it won't be long before what we call our commodity technology systems in the DOE, which are meant to be not nearly as challenging as these to port our codes to, typically Linux clusters and x86. I think we're going to start to see things like GPUs creep into those, because that's the goal of that program. So anyway, I'm going to get the hook here, so I better. All right, thank you very much.